Welcome to an exploration of one of chemistry's most counterintuitive phenomena, the sugar caramelization paradox. Sugar caramelization creates beautiful golden colors and complex flavors through a fascinating chemical transformation. Let's start by understanding what makes this phenomenon so paradoxical. Pure sucrose begins caramelizing at temperatures between 160 and 180 degrees Celsius, a relatively high temperature. When we add water, or acid, we actually lower the temperature of the sugar mixture. But here's the paradox. Caramelization happens much faster despite the lower temperature. This seems to violate our intuition about reaction rates. Here's the comparison. Pure sugar at 180 degrees caramelizes slowly, while sugar with acid at only 140 degrees caramelizes rapidly. Temperature alone doesn't tell the whole story. To solve this paradox, we need to understand sugar's molecular structure. Sucrose, or table sugar, is a disaccharide molecule composed of two simpler sugars, glucose and fructose, bonded together. We can represent this as sucrose equals glucose plus fructose. Visualize sucrose as two rings, glucose and fructose, connected by a glycosidic bond that holds them together. The key insight is that this glycosidic bond must break before the real caramelization reactions can begin. The hydrolysis reaction shows sucrose plus water yielding glucose and fructose, each with formula C6H12O6. Hydrolysis is the critical first step that explains our paradox. Hydrolysis literally means splitting with water. It's the process where water molecules break chemical bonds. At the high temperatures needed for pure sugar caramelization, hydrolysis happens extremely slowly without help. Without acid catalysis, only a few sucrose molecules get hydrolyzed. With acid, many more molecules are rapidly broken down into reactive monosaccharides. So what exactly do acids do to accelerate this process? Acids act as catalysts by donating protons, which dramatically increase the rate of bond breaking without being consumed. Quantitatively, acid catalysis can increase the hydrolysis rate by approximately 1,000 times compared to the uncatalyzed reaction. Let's examine this through the lens of chemical kinetics and the Arrhenius equation. The Arrhenius equation states that the rate constant K equals a pre-exponential factor A times E to the negative activation energy over RT. Here, K is the rate constant that measures reaction speed, A is the frequency factor. EA represents the activation energy, the minimum energy barrier that molecules must overcome to react. R is the universal gas constant 8.314 joules per mole Kelvin, and T is the absolute temperature. This energy diagram shows the activation energy barrier that reactants must overcome. The higher this barrier, the slower the reaction proceeds. Let's work through a numerical example for pure sugar caramelization. For direct thermal decomposition of sucrose, the activation energy is approximately 180 kilojoules per mole, quite high. That's 180 kilojoules per mole, or 180,000 joules per mole in standard units. At a temperature of 453 Kelvin, equivalent to 180 degrees Celsius, we can calculate the rate. The exponential factor becomes e to the negative 180,000 divided by 8.314 times 453, which equals e to the negative 47.8, approximately 10 to the negative 21. This incredibly tiny number explains why pure sugar caramelization at these temperatures is painfully slow. Now let's see how acid catalysis changes everything. With acid catalysis, the activation energy for hydrolysis drops dramatically to about 100 kilojoules per mole. That's 100 kilojoules per mole, nearly half the activation energy of the uncatalyzed reaction. Even at the lower temperature of 413 Kelvin or 140 degrees Celsius, we see remarkable acceleration. The calculation gives e to the negative 100,000 divided by 8.314 times 413, which is e to the negative 29.1, approximately 10 to the negative 13. Compare 10 to the negative 13 versus 10 to the negative 21. That's roughly 100 million times faster, despite being 40 degrees cooler. This visualization shows the dramatic difference. Fewer molecules react slowly at high temperature without acid, while many molecules react rapidly at lower temperature with acid catalysis. Water plays a dual role that's equally fascinating. Water serves two critical functions. It's both the reactant in the hydrolysis reaction and the medium that facilitates molecular interactions. You might ask, why does adding water help when it cools down the sugar mixture? The answer is that water directly participates in breaking the glycosidic bonds, the bottleneck that limits the entire process. Water molecules attack the glycosidic bond in sucrose, splitting it into glucose and fructose, which are far more reactive toward caramelization. Higher water concentration directly increases the hydrolysis rate according to mass action principles. In practice, optimal water content for rapid caramelization is typically 5 to 10% by mass of the sugar. Once we have monosaccharides, everything changes dramatically. Glucose and fructose possess reactive aldehyde and ketone functional groups that are chemically available. These functional groups undergo reactions like dehydration, fragmentation, and polymerization much more readily than intact sucrose. The cascade of caramelization reactions proceeds through dehydration, where water is removed, fragmentation, where molecules break apart, and polymerization, where they recombine into complex brown polymers. A typical dehydration step removes water, converting C6H12O6 into C6H10O5 plus water. Crucially, each of these caramelization steps has much lower activation energy than breaking the original sucrose-glycosidic bond. The process accelerates through a remarkable cascade effect. Once hydrolysis starts producing monosaccharides, it triggers a self-accelerating chain reaction. The products of early caramelization steps, including organic acids and other intermediates, actually catalyze subsequent reactions. This autocatalytic cascade resembles exponential growth, where one initial reaction spawns multiple secondary reactions, which spawn even more tertiary reactions. The overall rate becomes proportional to both product concentration and reactant concentration, creating positive feedback. This cascade effect explains why caramelization seems to happen suddenly, with rapid color change once it gets started. Let's make a practical comparison of actual cooking scenarios. When you heat dry sugar in a pan, visible browning typically starts around 170 to 180 degrees Celsius. Add lemon juice as an acid source, and you'll see browning begin at just 130 to 150 degrees Celsius. The temperature difference is substantial, 30 to 50 degrees Celsius lower with acid, yet the reaction proceeds much faster. Time to achieve golden brown color. Dry sugar takes 15 to 20 minutes, while sugar with acid takes only 3 to 5 minutes. That's approximately a 4 to 5-fold increase in reaction speed at a significantly lower temperature. Let's quantify exactly how pH affects the reaction rate. The hydrolysis reaction rate depends exponentially on the hydrogen ion concentration, which is determined by pH. Recall that pH equals negative log of hydrogen ion concentration, so lower pH means higher hydrogen ion concentration. The rate is proportional to hydrogen ion concentration, which equals 10 to the negative pH. This graph shows the exponential relationship. As pH decreases from 7 toward 1, the reaction rate increases dramatically. A pH 2 solution, like lemon juice, is 10,000 times more acidic than a pH 6 solution, creating vastly different reaction rates. Let's connect this chemistry to real cooking scenarios you might encounter. When making caramel sauce with cream, the cream's slight acidity actually accelerates the caramelization process. Crème brûlée works so well because sugar on the moist custard surface has water available for hydrolysis. Dry caramel making requires substantially higher temperatures and much more patience due to slow hydrolysis. Different caramel colors represent different degrees of caramelization. Light for subtle flavor, medium for balanced sweetness, dark for intense bitter notes. What exactly are the chemical products that give caramel its properties? Caramelization produces hundreds of different chemical compounds, creating complex flavors and aromas. Key flavor compounds include diacetyl with buttery notes, maltol with caramel sweetness, furans with nutty aromas, and hydroxymethylfurfuryl or HMF. A typical reaction shows dehydration continuing, removing 2 water molecules to form compounds like hydroxymethylfurfuryl. Products include large brown polymers for color, aldehydes for aroma, and organic acids that further catalyze the reaction. The characteristic brown color develops from high molecular weight polymers called caramelins, and caramelins. Let's examine the overall energetics of caramelization. Caramelization reactions are endothermic, meaning they absorb energy and require continuous heat input. The positive enthalpy change, delta H greater than 0, indicates energy must be supplied. You might wonder, why doesn't caramelization stop when we add cool ingredients? The answer is that once the reaction starts, it becomes highly exothermic, releasing heat and maintaining reaction progress despite cooling.